So in this video, I'm going to give a recap of how to analyze motor systems. So let me just briefly discuss the components that we have in our system. I'll start with the left-hand side, which is the electrical part of the system. So EA is the voltage that's applied to the motor. We then have a circuit that's connected to the motor. This here is the motor itself. So we've got a resistance. We've also got an inductance. Sometimes this is neglected because it's so small. And we also have a voltage drop across the motor itself, which we're calling VB, and the B stands for back EMF. IA here is the current that's running through this system. So we know that the input to a motor is the voltage, and the output to it is the rotation of the shaft. So the motor converts electrical energy into rotational energy. So Tm here is the torque developed out of the motor. And sometimes this rotational system is a bit more complex. I've just drawn a quite simple one. But we also have damping applied to the shaft at the output of the motor. J is the inertia associated with the shaft. Theta m is just telling us what direction we're going to measure the displacement of the shaft in. And of course, if you take the derivative of theta m, it's going to give you the speed, the angular velocity of that shaft. And if you take two derivatives, you're going to end up with the angular acceleration. So now let's discuss how we could actually go about analysing it. So the first thing that I recommend doing is to analyse the electrical system. So that's of course the circuit here on the left. And what I would recommend is applying the equation that the sum of the voltages in that circuit has to be equal to 0. So EA is the input. Everything else is going to drop voltage, so it's going to be negative. So it's going to be basically EA minus the voltage across this component, the voltage across this component, and the voltage across this component. So that's the first equation we can develop. Once we've got that, the next thing we're going to look at is our motor constants. Now, sometimes these will be given directly to you, sometimes they won't be. So let's write out the equations that we can use, and then we'll talk about how you can get them if you're not directly given the number itself. Alright, so this is the first one. So Tm is the torque out of the motor. Kt is a motor constant. This one here is known as the torque constant. Okay, and Ia is of course the current flowing through this circuit. The second motor constant equation we have is Vb, our back EMF, is equal to Kb. This is known as the back EMF constant. And theta dot m. So that's going to be the speed that this shaft is rotating at. The dot means it's the derivative with respect to time. So if you're not given Kt and Kb straight up, what you'll probably be given instead is a diagram that looks something like this. It's going to relate together the torque and the speed of the shaft. Sometimes this will also be written as omega m. It's the same thing. So you'll be given a curve, should be basically a straight line going downwards, and it will be measured at some input voltage EA. And there's two critical points that you're typically given on this curve, although if you have any 2 points on it, you will be able to use it. But usually you're given the stall point, which is this one here. It's stall because it's going to have 0 speed. And you're given this one, which is the no load point. And it's no load because you've got no torque coming out of your motor. So if you're given any 2 points on this curve, you can solve using these two equations, as well as the one that you've developed from your electrical system. So I'll do an example of that in one of the example videos as well. So once we've got our motor constants, we can substitute these equations back into the first one and start to eliminate some variables. So then we can move on to the third step, which is to analyze the rotational system. So the one that I've drawn here is very simple. It's only got one degree of freedom because we've only got this one inertia term. But if you have a more complex system, then you'll have to analyse it obviously in the more complex ways. So refer back to the videos showing you how to do those rotational system examples. But for this one, the only equation that you'll need to apply is that the sum of the torques have to be equal to J theta double dot. And this, of course, relates to theta m in our case. So once you've got those three steps gone through, the question basically just becomes a case of substituting everything into each other until you've eliminated enough variables down to the transfer function that you're interested in. So usually what we'll be going for is something that relates together the angular displacement of our shaft with respect to the input voltage, or otherwise you might be looking for the input speed with respect to the input voltage. Just remember, if you want to swap between these, it's really straightforward. Theta dot m is the same as theta ms when you transform it. So you can, substitute this into your equation if you need to swap between the two different forms. So that's all there is for this recap video, and I'll see you in the examples.